What if every decision you've ever made wasn't really yours to make at all? Hidden within the depths of black holes and the fabric of space-time lie mysteries that could rewrite everything we know about cause and effect. From grandfather paradoxes to wormholes bending reality itself, the universe holds secrets about time travel that even our greatest physicists still can't fully explain. Today we're uncovering 20 startling theories that blur the line between science and science fiction, ideas so bizarre they'll make you question whether the past is truly set in stone or if somewhere out there, another version of you already changed it. One of the most mind-bending ideas in physics comes straight from Einstein's revolutionary work. Time isn't as rigid as we once thought. His theory of relativity shattered the old Newtonian view, revealing that time actually stretches and warps depending on speed and gravity. Picture two identical twins. One stays on Earth while the other rockets through space near light speed. When the traveling twin returns, they'd be younger than their sibling, not by days but potentially years. That's time dilation in action, where motion and gravity slow time itself. Now take that idea to the extreme. Near a black hole where gravity is so intense it twists space-time like a whirlpool, time crawls at a near standstill compared to the outside universe. An astronaut orbiting just beyond the event horizon might experience mere hours while decades pass elsewhere. This isn't just science fiction, it's the universe's own rulebook, proving that time travel to the future isn't just possible, it's inevitable under the right conditions. Einstein's equations don't just hint at time travel, they demand it. General relativity shows how massive objects like black holes don't just bend space, they bend time, creating pathways where the future could unfold at different speeds depending on where you stand. The catch: there's no going back, at least not yet. While relativity opens the door to the future, reversing time would require bending the laws of physics in ways we still don't fully understand. But for now, the universe itself is proof. Time is far more flexible than our everyday experience lets on. Imagine stepping through a hidden doorway that instantly transports you light years across the universe or even into another era. Wormholes aren't just staples of sci-fi, they're serious theoretical possibilities lurking in Einstein's equations. Picture space-time as a vast sheet of paper, warped by massive objects like black holes. If you could fold that sheet so two distant points touched, a wormhole would be the tunnel punching straight through, bypassing the space between. The catch: these cosmic shortcuts would need something bizarre to stay open: exotic matter with negative energy, a substance that defies gravity instead of being pulled by it. While we've never observed such material, quantum physics hints that strange phenomena like particles popping in and out of existence might hold the key. Nature could even build its own wormholes near black holes where space-time twists into knots. Yet even if they exist naturally, passing through safely is another challenge. The moment anything enters a dust speck, the tunnel might snap shut like a rubber band, crushing the traveler in a blink. Scientists aren't ready to give up, though. Some theories suggest advanced civilizations could stabilize wormholes by threading them with cosmic strings or manipulating dark energy. Others propose they'd act like time machines, step in one end, emerge centuries earlier at the other. Until we uncover exotic matter or stumble upon a naturally occurring wormhole, these bridges through space-time remain tantalizingly out of reach. But if they're real, the universe just got a lot smaller, and the past might not be as far away as we think. But what if time travel isn't just about moving forward or taking shortcuts through space? What if time itself could curve into a loop, bringing you right back to where you started? This bizarre possibility isn't just fantasy, it emerges straight from Einstein's own equations. They allow for something called closed timelike curves, paths through space-time that circle back on themselves like a cosmic Möbius strip. Imagine tracing a line around a black hole so extreme that time warps into a closed loop. Step onto this path, and you could, in theory, return to the exact moment you left. No wormholes, no light-speed trips, just time bending until past and future touch. The idea gained traction when legendary mathematician Kurt Gödel solved Einstein's equations for a rotating universe. His solution revealed that in such a cosmos, space itself would swirl like water down a drain, dragging time along with it. Follow the right trajectory, and you'd end up right back in your own past. At first, even Einstein struggled with the implications. How could time, the relentless arrow of cause and effect, suddenly behave like a merry-go-round? Yet the real headache comes with the paradoxes. If you traveled back and prevented your own birth, how could you have existed to make the trip in the first place? This grandfather paradox isn't just a thought experiment, it's a glaring red flag that makes physicists question whether closed time-like curves could ever exist in our universe. Stephen Hawking famously argued against them, proposing the chronology protection conjecture, a cosmic safeguard that prevents time loops from forming, like some unseen law of physics snipping time's threads before they knot. But the debate isn't settled. Some theorists suggest quantum mechanics could resolve these paradoxes, with tiny particles looping through time without disrupting the larger flow of events. Others propose that closed time-like curves might only form under such extreme conditions, like near a spinning black hole, that they're practically impossible to access. Whether nature forbids these loops or simply hides them in the universe's most forbidden corners, one thing's certain: Einstein's equations keep whispering that time is far stranger than we'll ever see with our own eyes. What if you could build a time machine not from exotic matter or black holes, but from something as straightforward as a spinning tube of metal? Enter the Tipler cylinder, a concept so audacious it turns an ordinary object into a potential gateway to the past. Proposed by physicist Frank Tipler in the 1970s, this theoretical device hinges on one key ingredient: rotation at nearly impossible speeds. Picture a cylinder stretching infinitely through space, spinning so fast that it drags space-time along with it like syrup clinging to a whisk. According to Einstein's equations, this motion would twist the fabric of reality itself, warping time into a loop around the cylinder. Travel in just the right path around its surface, and you might find yourself returning to an earlier moment, a cosmic racetrack where each lap shaves years off your personal timeline. But here's the catch: Tipler's design demands perfection. The cylinder must be infinitely long to avoid gravitational collapse, and its walls would need the density of a neutron star to generate enough rotational force. Even a single imperfection, a dent, a seam, could unravel the delicate spacetime knot it creates. And while infinity is easy to sketch on paper, our universe has yet to reveal any object without an end. Critics argue the cylinder is less a blueprint and more a mathematical curiosity, proving time loops are possible in theory but laughably out of reach in practice. Yet its brilliance lies in its simplicity. Unlike wormholes or black holes, the Tipler cylinder suggests you don't need cosmic extremes to manipulate time, just raw physics and a machine built on scales beyond human engineering. For now, it remains a tantalizing what-if, a reminder that the universe's rulebook might allow time travel in ways we haven't even dared to test. At the heart of every galaxy lurks a monster so powerful it can twist time into a knot, a spinning black hole. Unlike their static counterparts, these cosmic whirlpools don't just devour matter. They churn spacetime itself into a vortex where the rules of time break down. Imagine approaching one close enough to skim its outer edge, the region called the ergosphere. Here, spacetime doesn't merely bend, it's dragged violently around the black hole like taffy in a machine, a phenomenon called frame dragging. The rotation is so relentless that not even light can resist being pulled along for the ride. This is where things get surreal. If you could orbit just outside the event horizon within the ergosphere, the laws of relativity suggest something extraordinary. Time for you would crawl to a near standstill compared to the rest of the universe. A few hours here might equal years elsewhere, a one-way ticket to the future. But what about traveling back? The math gets wilder. Some solutions to Einstein's equations hint that threading the needle of a Kerr black hole's rotation might create a path looping back into your own past. Picture slingshotting around this gravitational maelstrom at just the right angle, riding the twisted spacetime like a surfer catching a wave, except this wave could carry you backwards through time. There's a catch, of course, several actually. First, survival. The tidal forces near a black hole would stretch you into a human noodle long before you reached the ergosphere. Second, control. Once inside, the black hole's spin dictates your path, leaving no room for error. And third, paradox. If you did manage to circle back in time, the universe might enforce its own rules, like quantum mechanics stepping in to prevent contradictions. Yet despite the lethal risks, the idea isn't purely fantasy. Scientists like Kip Thorne have calculated that sufficiently advanced beings might harness a black hole's spin like a natural time machine, no exotic matter or infinite cylinders required. It's a reminder that the universe's most terrifying phenomena might also be its most ingenious engines, hiding temporal shortcuts in plain sight. The only problem: getting close enough to test the theory would be a trip with no return. Black holes were once thought to be eternal prisons, places where matter and light vanished forever. But Stephen Hawking turned that idea on its head. He revealed that black holes aren't completely black after all. They glow faintly, leaking energy over unimaginable timescales. This phenomenon, called Hawking radiation, suggests even the universe's most voracious monsters have an expiration date. Here's how it works. At the very edge of a black hole, pairs of particles spontaneously pop into existence, as they do everywhere in space. Normally, these particles annihilate each other instantly, but near an event horizon, one particle might fall in while the other escapes. The black hole loses a tiny bit of mass in the process, slowly evaporating like an ice cube under the sun. Given enough time, trillions upon trillions of years, even the largest black holes could dissolve into nothing but this faint glow. But Hawking's discovery has even deeper implications for time itself. Radiation carries information, and information is tied to entropy, the universe's measure of disorder. Normally, entropy only increases, defining time's one-way arrow. Yet Hawking radiation suggests black holes might scramble and eventually release the information they've swallowed, raising a tantalizing question: could that escaping energy hold echoes of the past? Some theorists speculate that if we could decode this radiation, we might reconstruct the history of what fell into the black hole, like playing a cosmic DVD in reverse. Others argue the information is lost forever, erased by quantum randomness. The debate touches on one of physics' biggest mysteries. Does the universe keep perfect records, or are some things truly forgotten? Hawking himself initially believed black holes destroyed information, violating quantum mechanics. He later changed his mind, but the puzzle remains unsolved. If radiation does preserve the past, it hints at a universe where nothing truly vanishes, just transforms. The answers might lie in the faint whispers of dying black holes, waiting for a future civilization advanced enough to listen. The universe might have its own way of keeping time travelers in line, not with force or barriers, but with a subtle rule woven into the fabric of reality itself. This is the essence of physicist Igor Novikov's self-consistency principle, a bold idea suggesting that the past isn't just fixed, it's bulletproof. According to Novikov, any attempt to alter history would be met with an invisible hand guiding events to ensure consistency. No paradoxes, no contradictions, just a cosmic script that's already accounted for every move a time traveler could make. Picture this. You travel back to stop your parents from meeting, armed with perfect knowledge of where and when they first crossed paths. But as you step into that critical moment, a sudden downpour forces you to take shelter, or a stranger bumps into you, making you drop the item you planned to use. Every move you make somehow fails to change the outcome, not by luck, but because the universe won't allow a contradiction. Your parents meet anyway, fall in love, and eventually you're still born. The past wasn't changed, it was always this way, complete with your failed meddling. Novikov's principle turns time travel into something like a predestination loop. Think of a filmmaker editing a movie. They can add new scenes, but the final cut must still make logical sense. In this view, time travelers aren't rebels rewriting history. They're actors playing roles that were always part of the timeline. Even their mistakes, a gun jamming, a warning ignored, aren't accidents. They're necessities, ensuring events unfold exactly as they already did. Skeptics argue this sounds suspiciously like fate, stripping away free will. But supporters counter that it's simply physics enforcing order. Quantum mechanics already shows particles influencing each other across time. Why not people? The principle doesn't forbid time travel, it just insists the universe won't tolerate plot holes. So next time you dream of altering history, remember, reality might have already written your part in the story, complete with all the times you tried and failed to change it. What if every choice you make doesn't just alter your future, it spawns an entirely new universe? This is the spine-tingling premise of the many worlds interpretation, where quantum mechanics doesn't just describe particles, it reshapes reality itself. At the quantum level, particles exist in a haze of possibilities, a superposition of states until observed. But what if this ambiguity doesn't collapse into a single outcome? What if all possibilities happen, each splitting reality into its own timeline? Now, throw time travel into the mix. Traditional paradoxes vanish when every decision branches into a fresh universe. Go back and prevent your birth. That act simply creates a new timeline where you never existed while your original world chugs on unchanged. Black holes might be the ultimate catalysts for this branching. Their extreme gravity could fray the edges of space-time, acting as cosmic routers shunting travelers into parallel realities. Imagine crossing an event horizon not to annihilation, but to a universe where history took a different turn, where dinosaurs never went extinct, or where you made that one pivotal choice differently. The math hints at eerie possibilities. Quantum fluctuations near a black hole singularity might amplify superposition, birthing new timelines like soap bubbles splitting in midair. Some theorists even suggest that Hawking radiation could carry imprints of these alternate worlds, like echoes leaking through the walls of reality. Of course, there's no proof yet. But if the many worlds interpretation holds, time travel wouldn't just be about revisiting the past. It'd be about surfing an infinite ocean of realities, each ripple representing a choice unmade or a chance untaken. The universe might not have a single timeline, but a sprawling, breathing multiverse where every what-if is already real somewhere. Forget rocket fuel. What if the key to time travel lies in stretching the very fabric of space itself? That's the radical idea behind Miguel Alcubierre's warp drive, a concept that sounds ripped from science fiction but emerges straight from Einstein's equations. Picture surfing on a wave, except instead of water, the wave is space-time, and you're riding it faster than light. Alcubierre's brilliant twist: your ship wouldn't move through space at all. Instead, the space around you would do the moving. Here's how it works. Behind your ship, space-time expands, pushing you forward, while ahead of you it contracts, pulling your destination closer. The effect: a bubble of warped space that carries you at any speed, even faster than light, without violating relativity, since you're not actually accelerating locally. Inside the bubble, time would pass normally for you while the outside universe zips by in fast forward. Combine this with time dilation effects, and you've got a potential time machine. Arrive at a distant star in weeks and return to an Earth centuries older. But there's a cosmic catch. Creating this warp bubble requires something we've never observed: negative energy, a mysterious substance that repels rather than attracts gravity. Current physics suggests you'd need a Jupiter-sized amount of it concentrated into a shell thinner than an atom. Quantum experiments hint that tiny amounts of negative energy might exist briefly at subatomic scales, like ripples in a quantum sea, but scaling that up remains pure theory. Some researchers propose workarounds, modified designs needing less negative energy or harnessing hypothetical cosmic strings. But for now, Alcubierre's drive sits at the edge of possibility. Still, it's a stunning reminder that the universe's rulebook might allow shortcuts we're only beginning to imagine. Who knows, the same physics that could one day send us to the stars might also hand us the keys to time itself. If black holes are the universe's ultimate one-way streets, white holes could be their cosmic exit ramps, hypothetical regions where matter erupts outward instead of vanishing forever. Picture a black hole's mirror image, an object so repulsive that nothing can enter, only escape. While no white hole has ever been observed, Einstein's equations suggest they're just as mathematically valid as their dark twins. Some theorists even propose they might be the other end of a black hole's tunnel, spewing out swallowed material into another time or universe entirely. Here's where it gets wild. If black holes warp time to a standstill, white holes might reverse it. Imagine a singularity not as a dead end, but as a cosmic turnstile. What falls into a black hole here could emerge from a white hole elsewhere, like water swirling down a drain only to burst back up from a fountain. This wouldn't just connect distant points in space, it could thread timelines together, turning a black hole-white hole pair into a natural time machine. Step into a collapsing star in one era, and you might find yourself ejected into a newborn galaxy billions of years in the past. But why haven't we seen these cosmic geysers? One explanation is brutal. White holes might be inherently unstable, flaring into existence for mere moments before collapsing under their own gravity. Others suggest they could exist only in the early universe, their outbursts mistaken for the Big Bang itself. There's even a fringe idea that our entire universe is the interior of a white hole, a spectacular rebirth from some other reality's black hole demise. The math dances on the edge of plausibility. For now, white holes remain ghosts in the equations, haunting reminders that the cosmos might hide exits where we least expect them. Whether they're real or just a beautiful quirk of theory, one thing's certain. If they exist, the universe's rulebook just got a lot stranger. Some of the universe's deepest mysteries might be hiding in plain sight, not in 3 dimensions but 2. The holographic principle turns our understanding of reality inside out, suggesting that everything we experience, space, matter, even time, could be nothing more than a projection, like a movie playing on the surface of an unseen screen. And where does this mind-bending idea take root? Right at the edge of black holes. Picture this: when matter falls into a black hole, it doesn't just vanish. According to the laws of thermodynamics, the information it carries has to go somewhere. But here's the twist: physicists discovered that all the data about what's inside a black hole, every atom and particle, might actually be encoded on its event horizon, the boundary where light can't escape. That's like taking every page of every book ever written and compressing them onto the cover of a single notebook. This led to a staggering revelation. If a black hole's 3D interior can be perfectly described by 2D information on its surface, could the entire universe work the same way? Some scientists argue that time itself might not be fundamental, just an emergent property, an illusion created by the way information interacts on a deeper, hidden layer. Imagine time as the hour hand on a clock, while the real mechanics are invisible gears turning beneath. If true, this reshapes how we think about time travel. Manipulating time wouldn't mean bending some cosmic river, it'd mean rewriting the code. A sufficiently advanced civilization might not need wormholes or warp drives. They could adjust reality's projection, tweaking the past like editing a holographic film. Of course, we're light years from proving any of this, but the holographic principle hints that the universe's greatest secrets might not lie in the vastness of space, but on the thin, shimmering surface of its darkest depths. What if you could hold time itself in your hand, not as a fleeting moment, but as a physical object that ticks like a clock? This isn't fantasy, it's the groundbreaking reality of time crystals, structures so bizarre they defy the fundamental laws we thought governed matter. Unlike ordinary crystals where atoms arrange in repeating patterns across space, time crystals pulse in predictable cycles through time like a drumbeat that never fades. First proposed in 2012 by Nobel laureate Frank Wilczek, the idea seemed impossible at first. Perpetual motion is forbidden by thermodynamics, yet time crystals achieve something eerily similar. Their atomic structures oscillate between states indefinitely without energy input, not by breaking physics but by exploiting quantum loopholes. Imagine a ring of atoms constantly flipping their spins in perfect sync, returning to their original arrangement at fixed intervals, a microscopic metronome that never winds down. The implications for time travel are staggering. If we could scale up these quantum ticks, time crystals might act as ultra-precise clocks for navigating distorted spacetime. A ship traveling near a black hole could use them to track time dilation down to the nanosecond, or even stabilize wormholes by syncing their rhythmic pulses to the warping of space. Some theorists speculate that advanced civilizations might already use time crystals as anchors, creating closed loops where entropy doesn't erode order, allowing information to cycle endlessly without decay. Recent experiments have turned theory into fact. In 2017, scientists created the first time crystals using chains of ytterbium atoms, their spins flipping like dominoes in a never-ending cascade. Later breakthroughs saw them engineered in diamond defects and even inside quantum computers. Each success hints that these structures aren't flukes, they're a new phase of matter lurking in quantum shadows all along. The real magic lies in what we haven't uncovered yet. Could time crystals reveal hidden symmetries in spacetime itself? Might they hold the key to decoding causality or even stitching together fractured timelines? For now, they stand as proof sometimes the universe's most profound secrets don't just bend the rules, they rewrite them entirely. Some stories write themselves, but what if they had no author at all? This is the chilling heart of the bootstrap paradox, a time travel conundrum where objects or information exist in an endless loop with no clear origin. Picture this: a time traveler hands Shakespeare a complete copy of Hamlet, inspiring the bard to pen the exact words he was just given. Who truly wrote the play? It wasn't Shakespeare, it just always existed, trapped in a loop with no creator, no starting point. Now take this eerie idea to the cosmic stage: black holes. Near the event horizon, where gravity distorts reality, information might not just disappear, it could recycle. Imagine a book falling into a black hole, only to re-emerge later as Hawking radiation, its pages scrambled but still intact. If someone retrieved and pieced it back together, they might unknowingly publish it centuries before the original was even written. The result? A paradox where the book's existence defies logic: no first edition, no original author, just an infinite loop of cause and effect folding in on itself. Physicists call these closed causal chains, sequences where events bootstrap their own existence. Einstein's equations allow for such loops under extreme conditions, like near a rotating black hole's twisted spacetime. The terrifying implication: reality might not always care about tidy origins. Black holes could act as cosmic recycling plants for information, churning out data that, from our perspective, appears to have no source. But here's the twist: quantum mechanics might have a solution. Some theories suggest these paradoxes resolve when tiny quantum uncertainties introduce randomness, breaking the loop. Others argue the universe simply rejects inconsistent histories, like a computer crashing from faulty code. Either way, the bootstrap paradox forces us to ask: is creativity an illusion? Could some of humanity's greatest ideas be echoes from futures that haven't happened yet? The answer might lie in the darkest corners of space-time, where black holes don't just consume information, they might rewrite it. What if the entire universe is crisscrossed with invisible cracks, defects in space-time so narrow, a single thread could outmass an entire galaxy? These are cosmic strings, hypothetical scars left over from the Big Bang, when the infant cosmos cooled unevenly, leaving behind fractures in reality itself. Picture space-time as a sheet of ice freezing over, regions where the structure hardened at slightly different angles, creating seams of immense tension. These filaments, thinner than an atom yet stretching across billions of light years, could be the universe's most elusive time machines. Richard Gott, a physicist at Princeton, uncovered their potential in the 1990s. His calculations revealed something astonishing. If two cosmic strings raced past each other at nearly light speed, their combined gravitational pull would twist space-time into a loop. Approach this slingshot just right, and you could circle back to your own past. No black holes, no wormholes, just sheer space-time geometry bending time into a closed curve. Here's the catch: cosmic strings, if they exist, are nearly impossible to detect. Their gravity warps light from distant galaxies in telltale ways, like looking through a cracked lens, but no confirmed sightings have occurred yet. And those needed for time travel, they'd have to be moving at unimaginable speeds, perfectly parallel, with no other gravitational interference. Even then, the window for a stable loop might last mere fractions of a second, a cosmic tightrope act requiring precision beyond our current reach. Yet the idea is tantalizing. Unlike black holes or wormholes, cosmic strings wouldn't demand exotic matter or infinite energy. They're relics of the universe's birth, woven into the fabric of reality. If we ever found one, or better yet, a pair, they might offer a path to the past without breaking a single law of physics. Until then, they linger as ghostly threads in our theories, whispering that the universe's earliest moments could still hold the keys to time itself. What if reality itself changes based on what we choose to observe, not just in the present, but retroactively rewriting the past? This isn't science fiction, it's the spine-chilling revelation of the quantum eraser experiment, where the act of measurement doesn't just record history, it can alter it. At the quantum level, particles like photons exist in a haze of possibilities until observed, a phenomenon called superposition. But in the delayed choice version of this experiment, scientists discovered something even stranger. Decisions made after a particle's behavior seem to ripple backwards in time, determining how it behaved before the choice was even made. Picture a photon traveling through a maze of mirrors and detectors. If scientists choose to measure which path it took, the photon acts like a single particle, leaving a clear trail. But if they erase that information after the fact using a clever trick called quantum erasure, the photon suddenly behaves as if it took both paths, like a wave. The twist: the photon's decision to act like a particle or wave appears to be influenced by the future, an effect physicists call retrocausality. It's as if the universe waits to settle on a single version of events until all the evidence is in. Now, imagine this effect amplified by the most extreme environment in existence, a black hole. Near the event horizon, gravity warps space-time so severely that time itself becomes fluid. Could these cosmic monsters stretch quantum weirdness to macroscopic scales? Some theorists speculate that within a black hole's grasp, retrocausality might not be limited to particles. It could rewrite entire sequences of events. A traveler crossing the horizon might not just move through time. They could blur the line between cause and effect, where actions in the future reshape the past like clay. The implications are dizzying. If black holes act as cosmic amplifiers for quantum retrocausality, the universe might not have a single linear timeline, just a vast web of entangled events, where past and future constantly negotiate what really happened. Until we can probe deeper, the quantum eraser experiment stands as an eerie clue. Time might not flow in one direction after all, but in loops, folds, and echoes, waiting for an observer to pin it down. Stephen Hawking wasn't just curious about time travel, he was suspicious of it. In the early 90s, he proposed something radical. What if the universe has built-in safeguards to stop paradoxes before they happen? He called it the chronology protection conjecture, a cosmic rulebook that might actively prevent time travel to preserve causality. Think of it as reality's immune system, detecting and eliminating paradoxes like a body fighting off germs. How would this work? Hawking speculated that quantum mechanics could act as the enforcer. Imagine trying to build a time machine. The moment it's activated, vacuum fluctuations, tiny, violent bursts of energy from empty space might surge uncontrollably, creating a feedback loop powerful enough to vaporize the machine. Or picture spacetime itself recoiling like a rubber band, snapping shut any wormhole before it stabilizes. These aren't random disasters, they'd be physics maintaining order, ensuring no event ever occurs without a clear cause. Scientists have even calculated scenarios where time travel triggers such extreme radiation that it becomes self-defeating. A single particle looping back through time could amplify into a lethal beam, frying the machine and its creator instantly. It's as if the universe has a kill switch for paradoxes, hidden in the fine print of quantum law. But here's the twist, not everyone agrees. Some physicists argue that chronology protection might only apply to certain types of time travel, leaving loopholes for subtle interventions that don't rewrite history. Others suggest this cosmic censorship could have gaps like a firewall missing patches. Hawking himself admitted he wanted to believe time travel was possible. He just couldn't find a way around the universe's stubborn defense mechanisms. One thing's certain, if the chronology protection conjecture holds, time travelers wouldn't just battle engineering challenges. They'd fight reality itself, a universe hellbent on keeping the past untouchable. Maybe that's why we've never met visitors from the future. The cosmos won't let them through. We've mapped the stars, probed black holes, and unraveled quantum mysteries, yet two cosmic enigmas still evade our understanding: dark matter and dark energy. Together, they make up 95% of the universe, invisible and undetectable except through their gravitational pull. But what if these shadowy forces do more than just shape space? What if they're secretly shaping time? At the heart of this idea is a simple but staggering question. Could dark matter and dark energy be the universe's hidden timekeepers? Near black holes, where gravity bends spacetime to its limits, their influence might become something stranger. Dark matter's gravitational grip could warp time in ways ordinary matter can't, like an unseen hand twisting the gears of a clock. Picture a black hole shrouded in dark matter. Its event horizon might not just trap light. It could stretch time into entirely new dimensions, creating pockets where seconds pass differently than anywhere else. Then there's dark energy, the force accelerating the universe's expansion. Some theories suggest it might not just push galaxies apart, it could be subtly altering the flow of time itself. In regions where dark energy dominates, time might thin out, speeding up like a river downstream from a dam. Near a black hole, this effect could twist causality into knots, making cause and effect flicker like a candle in the wind. Even more radical, dark energy might not just influence time, it could store it. Imagine if the energy fueling cosmic expansion also encodes information about the past, like a celestial hard drive. Black holes, acting as natural amplifiers, might tap into this reservoir, projecting fragments of history back into the present. Of course, this is all speculation, but that's the thrill. Dark matter and dark energy are blank pages in physics, waiting for a theory bold enough to explain them. If even a fraction of these ideas hold weight, the universe's greatest mysteries might also be its most powerful tools, keys to unlocking time itself. One of physics' greatest battles doesn't involve black holes devouring stars. It's about whether they destroy something far more precious: information. At first glance, it seems obvious anything crossing a black hole's event horizon vanishes forever. But here's the cosmic twist: quantum mechanics insists information can't truly be erased. Every particle, every interaction leaves an indelible mark on the universe's ledger. So when black holes evaporate via Hawking radiation, does that information escape, or is it lost forever? The answer could rewrite our understanding of time itself. Stephen Hawking initially believed the information was gone, a direct challenge to quantum theory that sparked decades of debate. Then came the holographic principle, suggesting black holes might store everything they consume as a scrambled code on their event horizons, like cosmic hard drives encoding 3D data onto 2D surfaces. If that's true, the radiation leaking away over eons isn't random noise, it's a slow, meticulous reconstruction of whatever fell in. Picture a library burning down, only for each book to reform one ash particle at a time in precisely the right order. This isn't just about preserving the past, it hints at bizarre mechanisms for retrieving it. Some theorists propose that under extreme conditions, like near a black hole's poles, space-time might project faint holographic echoes of that encoded information. Imagine gravitational ripples carrying whispers of long-lost events, replaying fragments of history like a cosmic instant replay. If we could decode those echoes, we might not just recover data, we could glimpse events from the other side of the horizon. Yet skeptics argue the holographic principle still can't explain how information escapes intact after being stretched and crushed by a singularity. Others suggest alternate solutions, like black holes birthing new universes where the information reemerges. The wildest idea, that black holes are natural time capsules, their interiors existing outside our timeline entirely, preserving moments like insects in amber until conditions allow their release. The paradox forces us to confront a profound question. Is time's arrow absolute, or can the universe stitch together broken sequences like a master editor? Until we solve it, black holes remain both the universe's most efficient shredders and its most enigmatic archivists. Deep in the cosmos's fiery cradle lies a theory so audacious it bends our understanding of existence itself. What if the Big Bang wasn't just the beginning, but a bridge? Some physicists now speculate that the singularity which birthed our universe might share a hidden kinship with black hole singularities, forming a vast, invisible network of cosmic time gates. Picture the universe like an endless hall of mirrors. Each black hole's crushing core could be a distorted reflection of that primordial spark, a tunnel threading through space and time to distant eras or even other creations entirely. The math hints at eerie parallels. Both the Big Bang and black hole singularities are points of infinite density, where gravity overwhelms all known physics. But while black holes trap matter, the Big Bang erupted outward, two sides of the same cataclysmic coin. Nobel laureate Roger Penrose proposed a staggering twist. These singularities might not be in points but portals. His conformal cyclic cosmology suggests that when our universe eventually exhausts its energy, all matter will decay into radiation, space will stretch smooth, and conditions will mirror the pre-Big Bang void, potentially triggering a new bang. Black holes, in this view, could be cosmic seeds, their singularities birthing fresh universes in their wake. Yet the challenges are as vast as the idea itself. Infinite density means our current laws of physics shatter like glass under a hammer. General relativity can't describe singularities, quantum gravity might, but we lack a unified theory to bridge these realms. Even if singularities are connected, traversing them would require surviving forces beyond comprehension, spaghettification, tidal rips, or worse. And if time loops through these gates, where does causality go? Does every black hole birth a new timeline, or are we just one thread in an infinite tapestry? For now, it remains a breathtaking what if. But if the universe's birth and death are linked, if every black hole hides a doorway, then time might not flow in a line at all. It could spiral outward in endless cycles where beginnings and endings are just two sides of the same impossible door. What if everything we experience, every star, every black hole, even time itself, isn't real, but lines of code in an unfathomably advanced simulation? This is the jaw-dropping premise of simulation theory, where the universe isn't a physical place but a digital construct meticulously programmed by some higher intelligence. And if that's true, then black holes might not just be cosmic anomalies, they could be glitches in the system, backdoors where the rules of time can be hacked. Think of spacetime as a vast, self-correcting program. Normally, it runs flawlessly. Gravity holds planets in orbit, light travels at a fixed speed, and cause and effect unfold in order. But black holes, they're like corrupted chunks of code, regions where the simulation's physics engine breaks down. The event horizon could be a firewall, hiding the point where reality's source code gets rewritten. Step inside, and you might not just travel through time. You could trigger a debug mode where past events are edited like variables in a computer script. Here's where it gets wild. If time is just data, then paradoxes aren't universe-breaking errors, they're patches waiting to be applied. A time traveler altering the past wouldn't create a contradiction. The simulation would simply recompile the timeline to maintain consistency, like a programmer tweaking an algorithm. Black holes might even be natural save points, where the universe stores backup states of reality. Fall into one, and you could emerge in a restored version of history, one where dinosaurs never went extinct or where you made different choices. Some physicists take this idea seriously. Nobel laureate Frank Wilczek has pondered whether black holes could be information processors, their singularities acting like cosmic CPUs crunching the code of spacetime. Others speculate that Hawking radiation isn't just random energy, it's the simulation's way of recycling deleted data, echoes of erased events leaking back into the program. Of course, there's no proof yet, but if simulation theory holds, time travel wouldn't require bending the laws of physics. It'd just take understanding the universe's operating system well enough to find the cheat codes. And if black holes are the glitches, well, they might not be the end of reality. They could be the ultimate tool for rewriting it. From the mind-bending fabric of relativity to the speculative edges of simulation theory, we've journeyed through 20 astonishing ideas that blur the line between science and the unimaginable. Black holes aren't just cosmic vacuum cleaners, they're the universe's most enigmatic laboratories, warping time, birthing parallel realities, and maybe even stitching together the past and future. Einstein showed us time is fluid, wormholes hinted at shortcuts through the cosmos, and quantum mechanics revealed particles that seem to remember the future. White holes, time crystals, cosmic strings. Each theory peels back another layer of spacetime's secrets, proving reality is far stranger than fiction. But here's the ultimate question: will humanity ever crack the code? Will we one day harness black holes as gateways, or will the universe's laws forever keep time travel just out of reach? The answers might lie centuries ahead, or they could be hiding in plain sight, waiting for a brilliant mind to connect the dots. Until then, the mysteries linger, tantalizing and just beyond our grasp. So what's your take? Which of these theories blew your mind the most? Drop your thoughts in the comments, because the greatest discoveries often start with a simple conversation. Who knows, the next big idea might come from you.